So the topic that's new that we have to cover today is something called half-life. And I've mentioned it a little bit already, this idea of how long does it take an unstable thing to become stable. And if you have a pile of it, it all doesn't happen at once. Over time, some of those atoms become more stable. And that's what half-life talks about. Now, Mr. Butters created a little reading for his students that I made copies of and left it out there. We're not going to go over that today. However, that is something that if this topic itself is a little confusing, feel free to look at that reading that he made, just that one-sided sheet of paper. I would rather us spend time right now going over that map that we have to be aware of. So that's the sheet. That was the last sheet you picked up on the way in. That was titled Nuclear Decay and Half-Life, the Map. And the top example is going to give you an example of carbon-14. One of the best examples that we have for this because we use that carbon-14 isotope to determine how long ago living things, if we dig up their bones later on, how long ago were they alive. I want to go over a couple of sample problems with you on this worksheet right now to show how to do this type of math. And if we halfway down start with question number 1, it says the half-life of TB161 is 7 days. How many grams of an original 300-gram sample will remain after 2 weeks? The term half-life means during that time frame, half of it will break down into something more stable. Now, the tricky part about that is after one half-life, half of it's now more stable and the other half still unstable. After a second half-life, it's not like it's all stable now. Only half of that remaining thing. So it's almost like those graphs that you would see sometimes in a math class where it starts here and then it's not a linear decrease. So I want to make sure we kind of understand that idea of half-life is you're never guaranteed to get every last bit of it to become more stable. It's just the odds of some of it changing over time is half of it over each half increment. Now, if I look at this problem, it says 7 days is one half-life and 2 weeks have gone by. Well, 2 weeks is 14 days. If I divide that by 7 days for one half-life, that means I'm going to have 2 half-lives occur. That's pretty simple math right there, right? How we suggest students set this up then. There's actually different ways you could do it. Actually, I could have written this division as a conversion of one half-life over 7 days. So we could have set it up like that, like we do for all conversions, but most people are pretty comfortable with just doing that division there. Write down the original amount of the sample that you're given. Recognize that it went through 2 half-lives. Now, I could show my work by dividing by 2 and stuff like that. We all agree, Knats, Butters, myself, that you don't actually have to show divided by 2. Instead, an arrow represents change in chemistry. So all we do to show our work is we draw an arrow to show that's one half-life. So I divided by 2, either in my head or use a calculator depending upon the numbers. And then it went through 2 half-lives, so 75 grams of it would still remain. That's all the math that we have for this. Now there's a couple different ways that you can go about doing it. We can give you the starting and ending values of something and you have to figure out the number of half-lives. And that's what question number 2 is going to go over. But at the end of the day, this is the work we want you to show. 2 half-lives, 2 arrows. And we like the arrow idea because if you count the arrows, it tells you how many half-lives there are. Some students will be off by 1 half-life because they'll just write 150 as their answer because they have 2 numbers there. That's why the arrow is a good thing just to keep track of it, yet we don't need you to write down divided by 2. Just like I don't need you to show me a metric conversion anymore. Some math we feel is very straightforward. If we look at number 2, again, number 2 slightly different. It says every 3.82 days. Let's stop there for a second. Comparing to number 1, which isotope do you think is more unstable? The TB161 or the radon 222? Radon 222. A shorter half-life means it must be really unstable and has to break down quicker. So it says that radon is going to decay into polonium-218. Letter A. How many half-lives will it take for 100 grams of radon-222 to decay to the point where there's only 3.125 grams left? 100 grams is my starting amount. I want to figure out how many half-lives will it take to get down to 3.125 grams. So what I would do is I divide by 2. 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 Until I got to the number that it asked for in the problem. Now there is a way you could set up with like a 1/2 to the x power and you're trying to solve for that exponent. I mean, if you want to show your work in that manner instead, I'd be fine with that because I know what you're trying to do there. However, this is simple. This is not calculator needed to divide by 2. Remember, if we're asking for the number of half-lives, you need to count the arrows then. 1, 2, 3, 4. There are 5 half-lives. Letter B asks for how many days is this? Well, if one half-life is 3.82 days, I just have to multiply that by 5 to give me 19.1 days. Finally, letter C. How many grams of polonium-218 will you have at this point? If the radon, the unstable thing, only has 3.125 grams left, I would subtract that from the original sample. Because remember, if I start with 100 grams of something, the unstable thing only has 3.125 grams left. But mass is still conserved, which means that subtracting these two will tell you how much of that daughter product and the remaining particles, I suppose, that are emitted would equal. So if I subtracted 100 minus the 3.125, that would tell me how many grams, 96.875. Of the more stable is produced. Because if you think about it, if I started with 100 grams of radon, I had 0 grams of polonium. In this problem it says that's the product of that decay. After one half-life, I would have 50 grams of each present. Again, assuming that the alpha particle is negligible for the mass that's being lost here. After a second half-life, 50 of this now goes down to 25. That means it lost 25. This would have gained more. So on and so forth down the line. So the point of that last question is to show you that during decay, whatever the original parent was, that mass is now being brought over to the daughter product. The point of half-life math is to show you that it doesn't happen all at once. There's a certain rate at which these types of decays occur. Now, if you flip to the back side, there's 2 other questions here. What I'd like to do is give you a start on number 3, but then have you try to solve that, and the same with number 4. So number 3 says, how many half-lives will it take for a sample to decompose to 1.56% of the original sample? What makes this problem a little bit different is it's not giving you a mass of a sample, it's telling you the percent that still remains. what percent would you start with? 100. So to give you a head start on this problem, what I would suggest doing is your divided by 2 math to figure out how many times do you divide by 2 to get to 1.56. That will tell you the number of half-lives that you have. Then in letter A, if it tells you that you have 400 years, you can multiply those to figure out your total number of years. And then letter B, well, if I had 726 grams, how much of that would remain? And then move on to number 4 with the uranium.